Okay, let's look at one more example and kind of tie all of this together. Consider the equation y squared equals x cubed minus 3x plus 1. Answer the following. Part A, find dy dx. Okay, so we can see this is an implicit equation because we don't have just y equals, we have this y squared equals. Okay, so let's go through and do our, go through these steps. So we've got derivative of y with, we'll take derivative with respect to x of both sides. So that gives me derivative with respect to x of y squared, and then a derivative with respect to x of x cubed minus 3x plus 1. Okay, so on the left-hand side, because we're taking the derivative with respect to x of this function y, we're going to have to use that chain rule. So it's going to be the outside function with respect to the, or evaluated the inside, so that's going to be 2y, times the derivative of the inside, so dy dx, equals, and then take the derivative of each of these pieces. So the derivative of x cubed is 3x squared, derivative of minus 3x is going to be minus 3, and the derivative of 1 is 0. So now to get the dy dx by itself, we'll divide both sides by 2y, and we'll get dy over dx equals 3x squared minus 3 all over 2y. Okay, so now if we're asked to determine the coordinate points where the curve has a horizontal tangent line. So horizontal tangent line, what's the slope of that? Well, that slope is going to be 0. So again, that derivative is the slope of the tangent. So we're looking for when that derivative is going to equal 0. So we found this as our equation for dy dx. So we are looking for when is this. So I've got 0 equals 3x squared minus 3 over 2y. So when is that going to equal 0? So let's first get rid of this fraction. So let's multiply both sides by 2y. And I'm going to get 0 equals 3x squared minus 3. So let's factor. We'll use that zero product property. So we're going to factor that 3 out. And then that again can factor into 3 times x minus 1 times x plus 1. And then we can set each of these equal to 0. So I get x equals 1 and x equals negative 1. So now let's go through and check this. So if we need to also find that y value. So if I solve this, let's see. So let x equal 1. All right, so when I go to my original equation and I solve this for y to find the y value there, I'm going to get y squared equals 1 cubed minus 3 times 1 plus 1. So I get 1 minus 3 plus 1, which is negative 1. Well, when I go to solve for y, that would be taking the square root of a negative, which does not exist. There's no real solution to it. So that means that this x ends up being an extraneous solution is what we call that. So an extraneous solution. So sometimes you're going to have that where you're going to find an x value that will make the function or the equation equal 0. But when you solve that for y to figure out that y value, there is no y value that gives an x value of 1. So again, this means there is no y value that has an x value of 1. So that is going to be extraneous. So let's hopefully, when x is negative 1, there are some y values so we can find those points, the coordinate points on the curve that has a horizontal tangent. So when x is negative 1, I get y squared equals negative 1 cubed minus 3 times negative 1 plus 1, which gives me negative 1 plus 3 plus 1, which gives me 3. So I've got y squared equals 3. So square root both sides, and make sure you remember when you square root, it's always going to be plus or minus. So that means there's 2 points on this graph that's going to have a tangent line. So those 2 points are when x is negative 1, it should be x is negative 1. When x is negative 1, y is negative root 3. and when x is -1 and y is positive root 3. So those are the 2 points that are going to have horizontal tangents. Okay, and then the last piece, determine the coordinate points where the curve has a vertical tangent line. So vertical tangent line, so let's see, so we've got the derivative of y with respect to x. So where are we going to have a vertical tangent line? So that's going to happen when, if I'm looking at this function, that's going to happen when this equals the derivative is infinity or negative infinity. That's where we're going to have that vertical tangent. So to get infinity or negative infinity, this denominator has to equal 0. So we need to solve for when that denominator is going to equal 0. So 2y is going to equal 0 when y is 0. Great, so now I know at least the y value, and let's solve for the x value. There might be more than one. So we've got 0 squared equals x cubed minus 3x plus 1. So 0 equals x cubed minus 3x plus 1. So at this point, and I will add this to the directions, you can use like a GeoGebra has a computer algebra system that will allow you to solve this equation. Same with your calculators if you want to use that. So if you throw this into any of those CIS systems, you'll end up getting that x is approximately negative 1.88, 0.35, and 1.53. So the equation, or the coordinate points that are going to have a vertical tangent are going to be at at x equals negative 1.88, y equals 0, 0.350, and 1.530. I'll show you how to actually solve this using Desmos on that next page, and then also how we can go through and actually see if this is the true case. So next slide, I'll go through that. Okay, so you can see here I'm in Desmos and I've typed in the equation y squared equals x cubed minus 3x plus 1, and it produces this super cool graph. So if I'm trying to see where this is going to equal 0, so it's where's this y value going to be 0, I can see right about at those points. But if I want to know those exactly, what you can do is actually just click on the graph itself and you'll see it'll give you those exact values. So that's where that negative 1.88 comes from, the 0.35, and then the 1.53. So you can see those points right there. The other thing that you can do is you can just set in a second equation where we're solving for when y equals 0. So if I just graph that line y equals 0, I can see where that line y equals 0 intersects the graph y squared equals x cubed minus 3x plus 1. So I'm essentially saying, okay, let's let this equal 0 and see where those two graphs intersect, and that's going to happen at those x values. So that's another way to do it.